Hi folks, this time we're going to do an Atwood machine problem. A little history. There was the Reverend George Atwood, and Atwood lived in the late 1700s in London. And he was a reverend. In his spare time, he built a device that was a big pulley attached to some ropes, and he did an awful lot of experiments with this apparatus looking into the laws of motion. Reverend Atwood's contributions to science are considered so important that there's actually an Atwood crater named after him on the surface of the moon. So that's kind of cool. But this is a picture, something kind of like a small plate as a pulley. The rope has almost no mass, and this whole apparatus is free to spin with almost no friction. And what's going on is this. On the left side, I'm going to call this mass 1. I've got a weight of 0.55 kilograms. On the right side, I'm going to call this mass 2. I've got 0.800 kilograms. And it's suspended. If you want to think of both of these weights sort of supported before we begin, at a moment that we're ready to allow the motion to occur, the weights stop being supported and the whole system will pivot. Now look at this. Which direction do you think the whole system is going to turn? Towards the 0.55 or towards the 0.8? When you remove both supports, the whole system is going to turn in the direction towards the 0.8. The force of gravity on the right side will be greater than the force of gravity on the left side. Now remember, we said the direction of motion we're going to call positive, and anything that goes in the other direction we're going to call negative. So here are our two weights. We're going to draw the forces on both masses. This is going to be the force of gravity on block 1, and tension is going to pull upward. This is going to be the force of gravity on block 2, because they have different masses, different forces of gravity, but they are attached to one rope, and there's no slack in that rope, and so the tension is going to be the same throughout. The next step is going to be to sum the forces on both blocks. So the sum of the forces on block 1 are going to make mass number 1 accelerate. The sum of the forces on block 2 are going to make mass number 2 accelerate. So the sum of the forces on block 1, let's make our equations. So block 1, tension is in the positive direction because it's pulling around clockwise. And we said that we're going to call positive in this problem. So tension minus the force of gravity on block 1, because that's in a negative direction in our problem, from the reference frame that we have created, that's going to make mass 1 accelerate. The sum of the forces on block 2, force of gravity on block 2 is in the positive direction, minus tension, tension's in the negative direction, it's counterclockwise in this situation, is going to make mass 2 accelerate. Now we're going to replace force of gravity with mass times acceleration of gravity in both of these equations. So let's go ahead and do that. Tension minus force of gravity on 1 is going to be mass 1 times the acceleration of gravity, is going to make mass number 1 accelerate. Force of gravity on block 2 is mass 2 times the acceleration of gravity minus tension is going to make mass 2 accelerate. So there are our basic equations. Now we're going to throw our numbers in. Tension we do not know. Mass 1, whoops, that's a negative sign. Mass 1 is 0.55 kilograms times the acceleration of gravity, 9.8 meters per second squared, are going to equal the mass of block 1.55 kilograms times A. Let's simplify this by multiplying that through. And when I do that, 0.55 times 9.8, I get tension minus 5.39 newtons. Kilogram meter per second squared is going to be a newton, is going to be 0.550 kilograms times A. Now that is one equation, two unknowns, so I'm going to need a second equation to make this work. So let's go over to the other block and look at our equations for this right-hand block. Mass 2, and I'm just going to pull this down so I've got lots of room to write. Mass number 2 is 0.8 kilograms times the acceleration of gravity, 9.8, minus tension is going to make mass 2, which is my 0.8 kilograms, accelerate. There's my second equation. Let's simplify this. 0.8 times 9.8, this is going to be 7.84 newtons, minus tension is going to be 0.8 kilograms times acceleration. Two equations, two unknowns. Algebraically, this is solvable. Now, what we're going to have to do is solve one of the equations for an unknown and then plug it into the other. I'm looking for A, so I'm going to solve one of the equations for T. Doesn't matter which one you solve for. I'm going to solve the first one for T. So I'm going to solve this equation for tension so I can plug it into the other side. So tension here is going to be equal to 0.55 kilograms A. To get this on the other side, I'm going to add that to both sides of the equation, 5.39 newtons. Now that I have this, I am going to take all of this, plug it into this equation for tension. So let's go ahead and do that. 7.84 newtons minus tension. Now tension is all of this. 0.55 kilograms A plus 5.39 newtons equals 0.8 kilograms times A. Next, notice this negative sign. I have to distribute that negative sign through everything in parentheses. So this is going to turn into 7.84 newtons minus 0.55 kilograms times A plus a negative, so I'm just going to make that a negative, negative 5.39 newtons, because I'm distributing the negative sign through, is 0.8 kilograms times A. And when I'm trying to be speedy, sometimes I forget some of those zeros in my sig figs. Now my quest is going to be to get everything that is like terms on the same side. So I'm going to try and get all of the A's over here, and I am going to get all of the newtons over here, which they already are. So let's simplify this. 7.84 newtons minus 5.39 newtons. The left side turns into 2.45 newtons. And on the right side, I have 0.8 kilograms times A plus, because when this moves to the other side, the sign changes, so plus 0.55 kilograms A. So the right-hand side turns into 1.35 kilograms times acceleration is going to equal 2.45 newtons. One last division and whoo-hoo, we are done. So acceleration is 2.45 newtons divided by 1.35 kilograms, and I'm going to end up with 1.81 meters per second squared is the rate of acceleration of the entire system because they're tied together and there's no slack in the rope. All right, that'll do for Atwood. See you later.